Almost there. We can get started. Yeah. Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's speaker featuring Dr. David Fridovich-Keil. Dr. David is an assistant professor at the University of Texas at Austin. David's research spans optimal control, dynamic game theory, learning for control, and robot safety. While he has also worked on problems in distributed control, reinforcement learning, and active search, he is currently investigating the role of dynamic game theory in multi-agent interactive settings such as traffic. Professor David's work also focuses on the interplay between machine learning and classical ideas from robust adaptive and geometric control theory. Dr. David, thank you so much for taking the time this morning and spending for this webinar. I appreciate sincerely your effort and time, and I think we're great honored to have you on, as part of the webinar series. The floor is yours, and you can go and share your screen.
Okay, well, it's fantastic to be with you guys. Thanks so much for having me. Let me get the screen share going, and we can start off as soon as I can find the right window. Hold on, give me one hot second.
Sure.
Okay, looks like I got to take this. Oh. Turns out you cannot share your screen if you're already in presenter mode. So let's.
Oh.
Okay, there we go. Okay. All right. Hopefully that worked.
Yes, sounds good.
Okay, fantastic. Okay, so again, thanks for having me. And so today I'm going to tell you about, I guess, a line of work that's been going on in my group for the last several years. So the general theme is going to be game theory, but the specific, I guess, the specific direction I want to be investigating here in this talk is the role of information when you're designing algorithms to solve games. So I think you'll see exactly what I mean throughout the talk, but this talk is structured roughly the first third or so is almost a tutorial. The next third is a fairly deep dive into some of the kind of mathematical foundations for exactly what I mean here about information and algorithmic design. And then the last third is going to be some, hopefully broader outlook on what can we do with these tools that we've now developed. So that's the plan. All right. I'm talking about games, so I want to give you maybe a concrete sense of what I mean. So games appear in all kinds of application areas. I'm showing just some snapshots of a few. Excuse me. So, whether you care about, say, power systems with renewables or routing of aircraft or traffic on the left, all of these things have multiple decision makers, and there's some actions that they can take which influence what one another see in the future and have to deal with in the future, and therefore influence kind of future decisions of other decision makers. So at heart, that's kind of what a game is that's played over time. And so these are what we're going to call dynamic games. Anyway, so these appear all over the place. In this talk, I'll focus in on traffic as just kind of a running theme, but you can hopefully be able to translate anything I say about that to, what other application areas you may care about. So in the context of traffic, it's very natural to think about decision making here in terms of, say, model predictive control. So so what I mean there is if you're, say, one of these cars, you are gonna think about the decisions you're going to make in the next few seconds as an optimization problem, and then you're just going to solve that problem, decide what to do, take a few steps, and then look around you, see what changed, and resolve a similar problem a few seconds later. So that's model predictive control in a nutshell, and you can kind of think of the game theoretic tools and algorithms we'll be developing in this talk as maybe an analog to a multi-agent analog to this model predictive control worldview. So I want to show you a little bit of what I mean there. So in this model predictive control viewpoint, you're the black car here, you're trying to make a lane change. What do? You basically, you look around you, you decide, okay, based on the lane geometry and where the other cars are and whatever else, I'm going to cook up an objective function J here. that depends on my actions U in the future and the corresponding states of my vehicle X in the future. Okay. Now I can't just pick any states X and inputs U. I have to pick them so that they satisfy some constraints, right? So here I'm just putting down the simplest constraints you got to satisfy. You got to be feasible, physically feasible, dynamically feasible. You got to satisfy the kinematics of the car. But you've also got to start at the proper location where you are now. You can't start anywhere you like. So you have to satisfy these two constraints. There may be lots of other constraints, actuator limits, what have you. But anyway, it's an optimization problem. You solve it, get a trajectory output. That's what I'm illustrating with the arrow, and you're off to the races. So that's kind of the starting point. But in reality, there are these other cars out there, and each of their decisions in the future is going to impact your objective. So here, what I'm writing out is the state trajectories of agents 2 and 3 in blue, X2 and X3. Those those ought to factor into the black car's decision making, right? So here I've written it as incorporated it into the objective for the black car. Okay, so anyway, so still an optimization problem. It's just a little bit more complicated now. But where we're going to go in this talk is to basically take a next level view here and try to understand where do these X2 and X3s come from. Well, they're trajectories of agents 2 and agents 3, and these guys are making decisions themselves. So really what's going on here is there's, for these 3 cars, each one of them is solving an optimization problem, and the output, the decision that each one makes as a result of its problem is an input to the other player's problems. So if you look here, player 1, agent 1, it depends on what agents 2 and 3 do. Agent 2, its problem depends on what agents 1 and 3 do, and so on. So these are really coupled problems, coupled optimization problems. And as soon as you have coupling among decision makers, you should immediately start to think of a game. So that's where games arise. Okay, so hopefully that instantiates the problem very concretely. Let me build some of the, I guess, mathematical formalisms for us. So, okay, what are we actually talking about here formally? Well, a dynamic game is a game that's played over time. There are objectives. I'm going to denote these J, superscriptively player. And because it's played over time, there are rules to the game. There are dynamics. And so these basically determine how states of the game evolve depending on the inputs. So states are going to be X, inputs are going to be U. I'll bold things to denote kind of aggregation over time. Anyway, so these are the kind of 2 main ingredients, but there's a missing third one. And the third one is really the heart of this talk. So the third one is what information is available to each player when they have to make a decision. If you can imagine, like, think about driving, and you could think about framing like the game we just saw on the previous slide. It's 3 cars interacting in traffic. You could think about framing it maybe at 2 extremes of this information landscape. You could think about it on one extreme as every player gets to see everything about what the other guys are doing when they make a decision. So that's a pretty decent model of how we drive. I drive with my eyes open. I look around at the other drivers on the road, and I know that 3 seconds from now, when I have to make that left turn, I'm gonna get to see where the other guys are at that point. So that's one kind of information structure to the problem. Another one would be, well, I'm gonna look around now, see where everybody is, and then I'm gonna close my eyes and know that in the future, I will never have my eyes open again. So I'm just gonna have to decide what to do now and play it out kind of in open loop in the future. So those are 2 extremes, clearly, and you could imagine other things in the middle. So information structure determines kind of what strategies can be played by different decision makers, and that is going to have a strong influence upon solutions to the game. Okay, so that's where we'll be going. We're going to see how this information structure factors into solving games. Okay. All right. The last thing to mention, just in terms of set up is we're going to be looking for a Nash equilibrium in this talk. There's all kinds of other equilibrium concepts in games, some of which we've studied, many others we haven't. But Nash equilibrium concept is the kind of simplest, most classical one, and it basically just says you're at a Nash equilibrium if, given every other agent's decision, every other agent's strategy, you would not like to change your own. So that's a Nash equilibrium, and I'll show you more as we go forward. So let's put this back in the context of that traffic example. Here's just a different intersection geometry. Again, 3 decision makers. You could write down the dynamics just by writing down the kinematics of a car or a model of a pedestrian or whatever. So keep track of things like position, speed, headings, etc. For each player. The objectives, there are all kinds of ways to model what drivers or pedestrians might want. But here's a few kind of, think of them as basis functions if you like, but there's all kinds of ways to model this stuff. Here I've just said, maybe you could imagine that players don't want to deviate too far from their lane centers, that they want to respect the speed limit, they want to not get too close to other agents, that kind of stuff. And then as far as specifying information, what I've written here is that player i's decision at time t, that's UIT, is some function gamma of the full state xt, meaning player I at time t knows that he's going to get to see the entire state of the game, where every other player is at that time. So that'd be called a state feedback structure. All right. So it's fairly straightforward to instantiate a game to make each of these 3 elements concrete, which of course leads us to the question, how do we solve a game? All right. Before we get there, I want to just give a very quick historical interlude. I find the history of this stuff very fascinating, and if anybody's been exposed to this kind of literature before, I think you'd probably agree with me. This is one of the most fun books to read. At least the first couple chapters are fantastic. This is so anyway, all of this literature in dynamic games dates back to one person, Rufus Isaacs, who's the fellow in the bottom right here. And the theory that it was actually developed in the late 40s. The first publications that at least I've been able to find were in the very early 50s, in a series of 4 like tech reports from Rand. But anyway, if you think about the timing, this was actually right around when Nash's Nobel Prize paper came out in 1950. So this was really all happening around the same time. And the interesting part, one interesting part, is that this theory of dynamic games was really developed in the defense context. It was not economic at all. It was you can literally read the title of the book here, but applications to warfare and pursuit, control, and optimization. So all the examples here are fairly military oriented for better or for worse. But anyway, his history is interesting, and he gives all of these great examples of games which, because this was the early 50s, he was focusing on problems that you could actually solve analytically. So there's a couple interesting ones I want to point out to you. So the first one, I don't think he gave it this name, but this is how I've heard it described, as a nuclear bomber problem. But imagine you're the fighter. There's a bomber, and you're trying to, you, the fighter, are trying to shoot down the bomber before it gets, too close to your country border. And so the, border can look whichever way you like. What's the right strategy here, right? So what's the Nash strategy and in feedback strategy? So let's instantiate those 3 elements of a dynamic game. Okay, so first question is, what are the objectives of the players? Well, the fighter wants to, in this case, the way he posed it is the fighter wants to get on top of the bomber, exactly on top, and do so at a point at which the bomber is as far away from the country border as possible. Okay, and at which point the game is going to end, because the fighter will have shot down the bomber. And then the bomber's objective is just the reverse. It's just the negative. So basically, get as close to the border of the country before you get shut down. The next thing is the dynamics. So what are the dynamics here? In this example, the assumption is very simple. It's just that each of these aircraft can basically go at a fixed speed in any direction. So that's pretty simple dynamics. And as I said, this is state feedback. So that's the information structure. At each time, both aircraft are going to get to see where the other one is. Turns out in this case, there's a really elegant geometric solution, and it looks like this. Basically, you draw a line between the two, you draw the perpendicular bisector, and then you find the point on this perpendicular bisector, which is as close as possible to the border of the country. Okay, and if you think about this point, what's true at this point is that this is, anything above the perpendicular bisector, the bomber can get to before the fighter. And vice versa below the line. So this red point is the point, is the closest point to the country, which the bomber can get to, at the same time as the fighter, right? So turns out it's not so hard to prove that the equilibrium strategy here is for both players to figure out where is this point and then go straight towards it. So that's what ends up happening. Okay. Nice geometric answer. There's all kinds of other ones. Another of my favorites, and probably most people in this space, their favorites would be called the homicidal chauffeur problem, which is about what it sounds like. There's a car that can control its yaw rate. And it's basically the question is what's the right way to run down a pedestrian? If the pedestrian can just, go at a fixed speed that's slower than the car, but choose its direction at will. So anyway, it turns out that problem also has an analytic solution, which is pretty elegant and involves this kind of swerving maneuver that I'm illustrating here in this figure. So, so there's a long history to these problems, these dynamic games. Ooh, there's a question.
I think we can have the Q&A after the session.
Okay, great. No problem. Okay, so anyway, there's a long I guess 70-year-old literature in this area now, and it's I find it fascinating. If you're at all interested in it, I highly encourage you to check out that book. I'm happy to give the reference to anybody who's interested, and it's a great read. So, okay, with all that said, these were from the early 50s, and I'm talking about the 2020s. So, what has changed? Okay. So I think the biggest, at least most interesting part to me is what's changed with respect to algorithms for solving these problems. Okay, so how do we go about solving them? Well, the first thing, and this is an old result that dates to the late 60s, is that global feedback Nash equilibria, sorry, this actually, what am I saying? This actually dates much earlier than the late 60s. The global feedback Nash equilibria, they correspond to solutions of coupled partial differential equations. Actually, that book I just showed you from Rufus Isaacs, what he developed was specifically the zero-sum variety of this, which has a kind of a special case, special structure there's a single PDE. So anyway, you should be thinking about partial differential equations as kind of the specification for a solution, at least in kind of the continuous time setting. And as soon as you think that, you should probably immediately think, well, there's going to be a curse of dimensionality involved with solving these PDEs, and that's going to be painful. So indeed, yeah, that's true. And so there's been a lot of work in the last 70 years to try to, of course, push on methods to solve these PDEs in what cases we can handle, to identify special cases of stable dynamics, the objectives, the constraints, which we can solve again maybe analytically. So those have kind of been, I'd say, the primary directions of research in this field. But what's happened in the last, let's say, 5 to 10 years is I think an entirely different direction. So that's what I'll be focusing on for the rest of this talk. So what's happened, I guess what's happened in the last 10 years, let's say, is people have become more interested in different types of solutions than what are called global Nash. And what I mean here is, in the same sense of a local optimum in an optimization problem, you can define a similar concept of local equilibrium in a game. And turns out that those points are ones which we can find much more simply. So, so let's see how to do that. Think back to those coupled optimization problems we saw before. So I've just rewritten them here with a slightly different notation, but it's these are the problems. Each of n players, n agents, is solving one of these optimization problems. The first thing that comes to mind that you might imagine doing is just solve each player's problem, in sequence, fixing the other player's strategies. So this is really old. It's called iterative best response, and sometimes it works. There are totally types of games where this will always converge, but there are many where it won't. And one of the classic examples of problems with this would just be rock, paper, scissors. It's the simplest game you can think of, right? So in rock, paper, scissors, if I start by saying I'll play rock, then of course you're gonna want to play paper. I'm going to say, no, you're playing paper. I definitely don't want to play rock anymore. I'm going to play scissors. And we're just going to go kind of around and around and around. So this iterative best response scheme is intuitive. Sometimes it works, but also sometimes it doesn't. So anyway, this should, make us think of something better. So let's try again. What do we do? Well, if you stare at optimization problem like this, you should probably have an immediate kind of knee-jerk reaction if, especially after like taking an optimization course or something. I don't know if there are students in the audience right now, but if you're a student and you say recently took a convex optimization course, you'd stare at this and you'd say, aha, I should write down the KKT conditions. So if you write down the KKT conditions for each player, each agent, and sort of just concatenate all of them, stack them all up, you'll get somewhere like this. So here I've written, I've introduced Lagrange multipliers lambda for these constraints. And I've written down the Lagrangian. I've taken the gradient of the Lagrangian with respect to the primal variables for each player, stacked all that up, enforced these equality constraints. There's no inequality constraints in the problem the way I wrote it. So we don't have to worry about complementary slackness or anything like this. And anyway, so all the KKT conditions boil down to a big nonlinear system of equations. So some the primal variables x and u, the dual variable lambda, some function of these three things must equal 0. That's what the KKT conditions boil down to here. So you can look at these and you can think, well, okay, if I can find a root of the map G, then I've at least satisfied every player's first order optimality conditions. And if you think about it, well, what that's saying is, each player is, to first order at an optimum. There may be some curvature issues, some second order sufficiency problems, but at least to first order, when player one looks out and fixes everybody else's decision, player one is happy because they're at a first order stationary point. So you can solve these problems, find a root of G with any root finding method you like. Some variant of a Newton method would be good. And if you find such a point, it's called a local quasi-Nash equilibrium. It's local because it's based on derivative information. It's quasi-Nash instead of Nash because it doesn't account for second order curvature information. So all you know is that you're at a critical point. You don't know that you're at a minimum for each player. In any event, this is pretty good. And so if you add additional kind of curvature information about your problem, this is actually a pretty desirable point to be at. So so this gives us a roadmap to actually finding a solution efficiently because Newton methods are pretty fast. So anyway, so this is the building block. All right. So here's the good stuff. All right. Suppose I found a solution to suppose I found a local quasi-Nash point from the previous slide. Let's stare at this a little bit more. And I want to ask you, what information do players need to have in order to execute their strategy at such a point? So, I guess I don't know that this is this session is set up to take active Q&A, but think about it for a second. If you're player one in this case, and you look at a solution, an equilibrium that we just found, it's going to tell you a sequence of states, X, and a sequence of actions, U1 for player one, at equilibrium. And they're going to satisfy the dynamics constraints. They'll, to first order, be a solution, a minimizer of your objective, fixing everybody else's strategy. So what information do you need to have in order to play out that strategy? Okay, so I'll give a few more seconds. All right. Okay, so what information do you need? Well, basically, all you need to know is what time it is in order to play that strategy. So if I tell you, hey, it's time step 4, then you can go index into the U vector at the 4th index and say, okay, well, it's time step 4. I guess I should be playing the 4th entry of U for player I. Okay, so that's totally valid. And that's got a name. That's called open loop information. So this is an open loop strategy that we just found. And I gave an example. I kind of gave this distinction. I teased it a little bit at the beginning of the talk, but open loop information is like, imagine playing a game where you know that in the future you'll never get to see the state. You'll be playing with your eyes closed in the future. So that's in contrast to maybe I think a more natural way to play at least most games would be in a feedback structure to say, okay, I know that in the future I will get to look at the board. I will get to look at the state when I make a decision. So that's feedback. You know that you're going to have your eyes open. The naming is a bit unfortunate. Feedback, eyes open, open loop, eyes closed, closed. Anyway, so but the gist of it is there's these two extremes, and what we just found with this, find the root of the KKT conditions business is we found an open loop solution. So that's fine if that's a desirable way in which you'd like to play the game. But as I've kind of been hinting, this is not really the most natural way to, say, drive in an intersection. You typically want to make decisions with the knowledge that you will see you will see the state in the future when you have to make those future decisions. So same thing in chess. When I'm playing chess, I play with the knowledge that I will get to see the board 3 moves from now when I make that move. So so the question for the kind of next part of the talk is, how do we solve for feedback strategies locally? How do we still get the benefits of the local computation, the derivatives, and avoiding these PDEs and so forth, but still satisfy the feedback conditions? Okay, so that's where we're headed next. Let me try to illustrate for you a little bit of just why these solution concepts are so different. So here's an example. I should credit actually a colleague, Forrest Lane, who's at Vanderbilt, and gave me this example, but I think it's particularly elegant. So imagine it's 2 players. They're both going to drive like cars, so they can change their steering. They can accelerate, decelerate linearly, and the objectives are as follows. Player 1 wants player 2 to go to the origin. Player 2 wants to end up close to player 1. And both players don't want to exert too much control authority. They don't want to accelerate too much or turn too much. Okay, so question to you. So what I'm showing on the right is that player 2 is starting on the top, player 1 is starting on the bottom. Player 1 is starting kind of facing to the left with some initial speed. Player 2 is starting facing down with some initial speed. And the question to you is, which color corresponds to which type of equilibrium? Which color, blue or green, corresponds to a feedback or an open loop equilibrium? So maybe blue is open loop, maybe blue is feedback. Same for green. Take a minute to think which is which. How would you play the game? Let's take feedback. How would you play the game if you knew that in the future you would get to see where the other guy is? Or an open loop, how would you play the game if you knew that in the future you would never get to see the other guy? You just get to see where they start. It's a bit of a brain teaser, but let me give it. So turns out feedback is green. So what happens here is that player one, the guy starting on the bottom, he knows that player two is going to see him in the future. And he also knows that player two is going to want to get close to him. So the rational thing to do here is to basically go towards the origin for player one. That's going to attract player two to the origin as well. Player one's going to then be happy because player two is at the origin. And player two is going to be happy also because player two got to be near player one. So, and they both had to exert some control, but presumably they can balance that out. And that's details. So, great. So that's feedback, and open loop is blue, therefore. So what happens here is that player one, again, the guy on the bottom, he knows that player two will never see him ever again. So they see each other at the first time step at t equals 1, but they're never going to see each other ever again. So that means that player one knows that nothing he ever does will influence player two because player two is never going to see it. So that means there's no way for player two to get player one to go to the origin because all player one's ever going to see is where he is now. So player two should just minimize his control effort. And in this case, he started facing to the left at some initial speed. So what that means is he's just not going to accelerate and keep going at a constant speed to the left. So that's what's going on at the very bottom of this figure. And then the other, the blue version of player two is going to, want to go towards player one. He only sees where player one is at first. He sees him facing left at some initial speed and basically makes a beeline to where he thinks he's going to end up. That's the best he can do. So, so I've hand waved this a little bit, obviously, but you can actually go through and just check for each of these cases, is player one's strategy in feedback, let's say, is there anything, let's player one strategy in open loop, is there anything better that he could be doing to minimize his objective? And you can basically just work out the KKT conditions and check that actually everything is satisfied here. So anyway, in pictures, you can see that these are two wildly different solutions that we just found. All we changed was the information available to each player at each time. And this tells us something. This tells us that, go back to that intersection I showed on like the second slide. I was talking about model predictive control as kind of a nice paradigm to think about decision-making here of looking out at the world, writing down some decision problem, solving it, taking a few steps of the solution, looking out at the world again, solving a new problem, etc. Well, what this example is telling us is that suppose you choose the open loop formulation of this problem. You choose blue. And you solve it. You take a few steps, so you're kind of following these blue trajectories, and then you take another look at where the other guy is and resolve the problem. It doesn't. You're never going to end up recovering the green solution if you do that. So what this example is basically telling us is that kind of the closing the loop with MPC, as it's often called, is really quite different from directly encoding a feedback information structure in the game. If you close the loop with MPC, quote unquote, you'll be solving for open loop equilibria, and you'll never get to green. So that's, I think, a neat little subtlety here. Here's another example just to show why these are so different. Think about driving again. If you want to be polite as a driver, a kind of natural way to encode that is to make yourself care about other people's effort. So, if you're trying to make a lane change, you should prefer to do so in a way that doesn't make the guy next to you have to slam on the brakes, for example. So how could you encode this really naturally? Well, you might take your original objective, let's say that's J1 tilde, that only depended on the state and your actions U1, and just add to it some norm of U2, of player two's inputs. Yeah, something like this. Well, if you do this, And then you look for an open loop solution. The next thing you're going to do, is you're going to write down the KKT conditions for player one. And you're going to realize that as soon as I take the gradient of the Lagrangian for player one, this term that I added, this norm of u2, it's just going to disappear because I take its gradient with respect to u1 and x1. And that's, it's a different variable. It doesn't depend, so it disappears. So my kind of attempt to encode politeness is just has no impact. The open loop equilibrium will not be affected by this, by this change. However, in feedback, that it's different. In feedback, what happens is we understand that player two's action, let's say at time 2, depends upon the state at time 2, which depends upon what player 1 does at time 1. So this derivative that I've x'd out in the open loop case is actually non-zero in general for the feedback case. So this is also giving us a sense that feedback structures are going to allow us to encode a more varied set of behavior. Okay. All right. So what is feedback? What is it actually? Well, I think there's a lot of ways to understand what it is in the context of these optimal decision problems. People often write down a tree, whether it's a single agent problem or a multi-agent problem. But so maybe we should start here. So if you think about a tree structure where time is kind of going vertically down, and each vertex in the tree is a state. Each arrow is a pair of actions or a tuple of actions for all the players. Then what's true in a feedback equilibrium is that at each subtree, every player is playing an ass strategy. So the way that naturally should lead us to think is if we work our way from the bottom of the tree to the top, we kind of need to be choosing actions at some arbitrary intermediate time, conditioned on the fact that future strategies will be in equilibrium with one another for each state that we might end up with. So this sub-game optimality or equilibrium property has a few names, actually. The one I prefer to use when introducing this topic is strong time consistency. So basically what that means is that if you imagine playing a game over some interval of time, and you imagine just finding yourself in some random intermediate time, at some random state. Is the strategy that you have chosen in the future, from that point into the future, part of a Nash equilibrium? Basically, given that, if we forget about what happened up until this point in time and we find ourselves at some arbitrary state, do we still like our strategies? If that's true, we're strongly time consistent, and we must be in a feedback strategy. So that's a couple ways to understand what is feedback actually encoding. But I think it's not immediately obvious how to build this into how to couple this concept, which is basically a dynamic programming type argument, with the KKT conditions and local optimality discussions we've been having so far. So let's see how to do that. Right. Oh, sorry. One other detail. I forgot to put this in. So one other interesting detail here. So if you look at this tree structure, what's going on, you can kind of distinguish between open loop and feedback just by looking at this tree if you are willing to draw these kind of dashed boxes, which is kind of an interesting quirky notation that people use in this space. But basically what this is saying is if you think of a game with particular dynamics, that will specify what the tree looks like, which vertices are connected to which others and by which arrows. But given a tree, you can specify what information each player has access to at each time. And the way that that's classically done is by grouping vertices which a player can or cannot distinguish among. So let me break that down. So look at the blue boxes. These specify a feedback information structure. And what they're saying is that at time 1, both players, basically they see the blue box, they know there's only one state in there. So fine. At time two, they know that they're going to be in one of those two blue boxes. And so basically at time two, let's say it happens to be the one on the left, there's only a single state in there, and they'll play as though they know exactly what that state is at that time. But compare that to the red box. So what the red box is saying is that at time two, the players will not be able to distinguish between the two vertices at that level. And same thing at the time step three, the players will not be able to distinguish between all four of the vertices here. So there's different ways you can denote, you can kind of encode these information structures, and this is a particularly common way to do it. In any event, the name of the game here is to try to encode feedback structures in a way that's amenable to local kind of gradient-based computation, because that will be efficient. So let's see how to do that. So the first thing to do is I'll work with a player's objectives which are time additive, like this. There are other structures that we could work with too. For example, it'd be fine if we had like a minimum of things over time or a maximum of things over time, but there has to be some time separability, and that'll, I think, become obvious in a minute. And then at time t, what I'm going to do is just kind of break that tree at some arbitrary state xt, and write down player i's problem for the sub game from there. Well, what player I is trying to do it from this state at this time is they're going to choose an action at time t, uit, which minimizes the cost right now, that's the first term in this sum, plus the best cost they can incur in the future. Okay. This is, say, if you've seen like a Bellman equation, this is exactly the same thing. There's a couple subtleties though, and I've circled the subtleties. So I guess what I'm imposing, let's handle the constraints at the far left here, the bottom left. So where my mouse is. Here, what I'm saying is that at time t+1, the action that every other player picks besides player I must follow its feedback strategy that's evaluated at the state that we happen to be at that future time. Okay. And then the bottom constraint is just saying that the state at the future time has to satisfy the dynamics of the game, the rules of the game. On the right, we have the same constraints, but they're evaluated, or they're imposed for all future times. So what's happening here is we're nesting. Everything is nested here, and you can immediately see it because I have the player's strategies here appearing in the constraints at future times, and these are kind of used in the definition really of player i's strategy at time t. So that's this function gamma it, the strategy at time t, depends upon the strategies for all the players in the future. And this is going to, recover that kind of nested tree structure we had on the previous slide. What's interesting is, by the way, if you write it down the way I just did and you eliminate the constraints in the boxes, everything collapses and you recover exactly the open loop game we had before. So it's the crux of the difference here is that I've broken things up and said what's going on at time t and t+1, and crucially I've imposed this recursive strategy constraints in the game as a constraint. Of course, also I've written it down just for player I, but every other player, every player has a version of this problem, and just like I showed on slide 3 or something, all the players' decisions are mutually coupled. Like player I's strategy at time t right here depends upon every other player's strategy at time t+1 and further into the future. So everything is coupled, and the inclusion of these boxed constraints is exactly the distinguishing factor between a feedback equilibrium and an open loop equilibrium. So this leads us to, okay, I've written down the problem. What are the KKT conditions and how do we solve for them? That's what we did in the open loop case. Let's do it in the feedback case. So, right, so this is that same business before. How do we write down the KKT conditions? Well, if you think about writing down the KKT conditions here, what's going to end up happening is that we're going to end up having to introduce dual variables, write down Lagrangians, take their derivatives with respect to primal variables. And so if you just think about this constraint that I'm circling with my mouse right now. So this guy is a constraint that has to do with this other players' strategies at time t+1. So I'm going to have to end up giving this guy a Lagrange multiplier, putting him into a Lagrangian and taking its derivative with respect to, in this case, the x variables. So I'm going to have to take the gradient of gamma minus I t+1 with respect to x t+1. Okay, but remember, this guy was defined in terms of gamma t+2 and into the future. So in order to take that derivative, I'm going to need to take essentially derivative out here. So I'm going to end up needing to take many derivatives, and they're going to nest in a unfortunate way is the gist of this. So ultimately, when you do all of that, all of these t levels of nesting are going to make it very hard to evaluate these policy gradients is what those are. So I'm just going to accelerate for the sake of time slightly, but the gist of it is, in order to do this, it's actually just totally wildly impractical to do this exactly for anything with more than a few levels of nesting. So what we did, and this is kind of the big enabler, it was just to say what happens if we totally ignore all the higher order derivatives here. If we just every place we see a policy gradient of order greater than 1, do we just assume it's 0? And if you do that, what you end up doing is, first of all, getting a very efficient algorithm, and second, changing the KKT conditions you're solving for. So in practice, what happens is you get something that looks like sequential quadratic programming. Here's like a little block diagram of the algorithm. If you've seen the iterative LQR, it's actually essentially the same thing. It's just that we're solving a game at that inner loop. So there's a lot of kind of nice classical connections that we're able to build to existing optimal control algorithms, but it actually works pretty well. So what you can do is, here's just a little Monte Carlo test. You can set up, like, here's a scenario of 3 people crossing a hallway. We just start the solver with a bunch of random initial guesses, run the convergence for each one of them, cluster the results, and you immediately see we recover 3 clean equilibria. And these, interchanged, these correspond to, players hugging the walls and letting the middle guy go through, or interchanging places and things like this. So the solver does work. We have some theoretical results that are trying to analyze the approximation error. I meant, of course, we're making this gradient approximation. So there are some more detailed results I'm happy to get into, but this short version is basically the solver is pretty fast. It actually runs in real time. So something I did actually, several years ago now, was go out to remote airfield in Washington and test on a Boeing, small Boeing test aircraft, just taxiing around the airport, trying to avoid taxiway intrusions and things, and writing all these trajectory optimization problems down as games, solving them in real time, no problem. Okay, so I recognize we're running pretty low on time. So what I'm going to do is just give you a quick flavor of how we've used some of these, basically this algorithm, and I think it'll give you a sense of the outlook that I guess I have, and many of my students also share. So okay, so now that we can solve these feedback games efficiently and often in real time, there's a few questions. So the first one is, what do we do when we don't know what other players want? So everything I've told you so far is kind of predicated on the assumption that we know what all the players' objectives are. But of course, in practice, if you're driving on the highway, you're not going to know exactly what every other driver wants. So turns out we can solve this problem, or we can at least do something intelligent here to figure out what are other players' objectives. So here I'm showing a case where there's 5 cars simulated driving on the highway. A couple of them want to make lane changes, and we'd like to infer a bunch of things about them. What are their preferred speeds? How far apart do they want to be? Things like this. All we get to see is the noisy position estimates on the right. We want to back out kind of cost maps on the left. So how do we do it? Well, you can write this down as an estimation problem. So we can basically say, let's assume we saw some noisy trajectory of the game. The players are playing a game, so these should be locally Nash. They should satisfy these equilibrium conditions we've been writing down. With some noise. How do we encode those? Well, we can just write down these equilibrium conditions as constraints on a maximum likelihood problem. So here's assume we have a sensor model. We can write down the likelihood of an observation given a state and an action. We can make some other assumptions about the sensor model here. I've just assumed it's like a additive white Gaussian noise model, so we get like nonlinear least squares popping out. And then these constraints, I wrote them down as though they're the open loop constraints. We've also done for feedback constraints as well, but you can impose these things, end up with a gigantic nonlinear program. There's great ways to, locally solve these things. Essentially, we can just pull a method off the shelf, sequential quadratic programming or something, and go for it. So what's the benefit? I'm telling you this as though it's something very easy. It's some direct corollary. Well, it actually has a pretty significant benefit. If you couple the problem together the way we did, what you end up doing is basically end up using those equilibrium conditions as a very strong prior on an otherwise under-constrained estimation problem. So the baselines here that we ended up comparing to were basically not exploiting this strong coupling between the game in the constraints and the max likelihood problem in the objective. So by exploiting the connection between those two problems, this thing I just showed you that was quick and easy corollary of everything we talked about for the last 45 minutes is just really beats down on the noise level here. So here what's happening is I'm simulating different levels of noise on the horizontal axis. I'm plotting some estimation errors on the vertical axis. It's a log scale, and you can easily see that doing things the way I'm suggesting, this additional prior information really helps. So you can, the message here is games don't necessarily, they're not restricted to being used as models of decision making. They can also be used as priors and estimation problems. We've done all kinds of variants of this. We've gone beyond maximum likelihood as an example. So here, this is like a kind of a variational Bayes kind of perspective. So using like a variational autoencoder to try to back out an entire posterior on these other players' objectives. Like I mentioned, we've incorporated feedback constraints in this game instead of just the open loop ones. Another thing, I mentioned this at the very beginning when I discussed the Nash concept, but there's other equilibrium concepts out there, and we've done some work with the Stackelberg equilibrium concept too. That's probably the second most common equilibrium you'll see in a game. This encodes hierarchy among players. So anyway, there's a bunch of other kind of neat directions that you can go as soon as you're able to solve games very efficiently. So hopefully this has given you a perspective on how to how to solve some of these problems, some of the recent advances in the field, and perspectives going forward. I'm happy to expand on any of these and take questions. So, oh, sorry, last detail. I forgot I had this slide. There's a really neat little mathematical fact which underlies a lot of the details that I've really glossed over today, which is that Nash equilibria, and it turns out Stackelberg equilibria too, are directionally differentiable with respect to parameters of a game. So what is this really saying? This is, like the high school calculus version of this is if you draw a circle and you write down the, equation of the circle, x squared plus y squared is 1. If you implicitly differentiate both sides with respect to x, you can rearrange and get a, expression for the derivative of y with respect to x. So we can do the same thing in higher dimensions and be careful with the conditioning of matrices and so forth. But basically, we can use this same implicit function theorem to back out derivatives of solutions to a game with respect to parameters of a game. And this is the the tool that we use all over the place. So anyway, that's all I had. Thanks so much. Yeah.
Thank you, Professor David. Appreciate for your time for this presentation. I think now we can take Q&A. I think I'm going to move Dr. Jin Lu to ask question. I think he has some questions. So can we move him as a panelist? Dr. Jin, you can ask your question. See if we can, yeah. Can you hear us?
Okay, thank you. I think I have already typed my question in the Q&A box, so that will make my question to be read more clearly. So to me, I feel that somehow, that might be your ultimate goal, is that you want to derive some numeric measure. So in your word, you call that to be trajectory. So you want to somehow trying to figure out the functional definition of such a trajectory that in order to make each participant to be able to locally calculate, how close, so or to evaluate, the distance values of the different of the distance values, of the various options. So am I correct that somehow the direction you would like to pursue?
I guess I'm not sure. Maybe I'm missing
Let me read his question.
Yeah.
I want to know how you will be able to generate a monotonically increasing or decreasing measure to each participant to evaluate the distance toward an equilibrium.
Oh, yes.
I would,
Okay,
I
that's
would
actually, yeah,
yeah.
sorry. Okay, sorry. I cut you off. Yeah, okay. So I think what you're getting at is actually extremely important point. So, the I'll restate my parsing of the question. So I think what you're asking is, suppose I'm at some intermediate point in the solve. So the solver's been going for some iterations, and I find myself somewhere. How do I know that the direction the solver wants to go next is moving me towards an equilibrium point? Okay, so this is actually quite subtle. This is okay, I'll give the answer first, and I think it will make sense, but I can also justify it a bit more. So the answer is, you can look at the KKT conditions and basically say how far, what's the, so this will be, remember it was a function g of x, u, lambda, or whatever. You can evaluate g. It's going to give you a vector in Rn, and you can just take the 2 norm square, right? So if that norm square is getting smaller, in some sense, you're closer to equilibrium. And when it's 0, well, it will, if it's 0, if and only if you're at a quasi-Nash. So that's an instance of a more general concept called a merit function. Merit functions are used all over the place in constrained optimization, and there's a whole slew of different ones people use both in the kind of standard optimization cases and these game cases as well. So anyway, the one I just described is the one we use. It's the simplest one you can think of pretty much, but it's not the only one.
So as you talked about that norm, does it mean that, adding to the second part of this question, to view the open loop information as a global function which evaluate the distance to the equilibrium? Is that?
So I guess the information itself is not a function per se. It's just a description of which states players can and cannot distinguish between at each time. So it's not exactly a function. And are you really working towards deriving a global function for measuring this distance? So I think as far as a global function for measuring distance, I mean, Euclidean norm, that's certainly a globally defined function. Now the question is, does it measure distance in a way that's actually monotonic? So like, how do I know that my solver is going to be making monotonic progress according to that function? That's a subtle point. So if you think about, well, the short answer is subject to some assumptions about conditioning of matrices. Basically, if the Jacobian of that map G, if that is full rank, I believe. Anyway, I believe, I forget the name of the result, but there's a result that's in like chapter 11 of No Sedal and Wright, something like this, that basically tells you there's a relationship between the condition number of that Jacobian and the like cosine of the angle between the step direction you compute and the gradient of that merit function. So basically what that's saying is like, if the condition number blows up, like your matrix drops rank, then the step you compute is orthogonal to the steepest descent direction on the merit function, which means you're not making monotonic progress anymore. So in practice, what this means, to cut to the chase, is if you regularize your thing a little bit, it's going to be fine.
We have another follow-up question. Thank you for that explanation. What is the computational complexity of a single interaction of iteratively solving a dynamical game?
I'm sorry. So the complexity of a single iteration.
Okay.
So, so you will solve the problem iteratively. And then, so I'm trying to know that, what will be the computational complexity, generally, for a single iteration, as well as that, whether, what will be the ballpark number of the iterations to be able to somehow to be able to reach reasonably close, okay, to the equilibrium. So is there any?
Yeah, I can answer those. So, so I guess the first most obvious thing to say is we're talking about Newton methods here, variance of Newton methods. So each iteration is basically solving a linear system of equations. So, it's going to be polynomial like cubic time in the size of these matrices in the worst case. But actually, in practice, it's nowhere near that bad, because like the number of variables is going to scale with the length of the time horizon. How long is the game played? There's additional variables at each time step. But if you end up writing down what all these matrices are, what Jacobians of KKT conditions are, is they're banded. So there's basically there's a very high degree of sparsity, and it ends up being like linear in the time horizon to solve them. But cubic, cubic, like if you're not using any kind of wacky large matrix factorizations here, but basically cubic in things like the number of state dimensions or the number of input dimensions, things like that. So that's the iteration complexity, or so that's the complexity per iteration. And then the number of iterations, the convergence rate, it's a Newton method again. So the convergence rate is superlinear typically. But depending on how non-convex your function is and how far away you start from a nice basin of attraction, you could be at a linear convergence rate for a long time before you get to superlinear.
Yeah, I got your point. So yeah, it will be really hard to be able to make the good estimate of the number of the iterations taken. But since your method is supposed to be used for guiding the drivers to make a very quick decision about how to divert or how to avoid some situation. So the time requirement, the response time will be very, very stringent. Then, so in that case, so how would you predict of the somehow the actual usability, okay, of this method to be able in the situation, to be for automated, driving of the applications?
Yeah, that's a great question. I guess I would say, like, I can just give you my experience. So my experience is I interned at a self-driving car company. That was actually how I got into some of this. At least the type of problems, if not the algorithm specifically. So there in that industry, from my experience and others that I know, typical solve times that you expect would be something like 10 hertz. If you're faster than 10 hertz, you're good. If you're slower than 10 hertz, something's not fast enough. So 100 milliseconds, I don't know, the code that I wrote as a grad student for like the very baby version of this solver, easily beat that. I mean,
And if I may also add a point, I think like you talked during a talk, the player strategies that you rarely know in the future times. And as you mentioned about, do we really know all kinds of combinations, actions that the players, that probably has some impact. And we don't know. The reaction time is a very good question. What Jen is asking, but
yeah. So the reaction time is fair, but I guess just strictly in terms of like how long do you have to wait until this thing converges? I think like it doesn't remotely concern me, at least in the specific context of self-driving cars with, let's say, I don't know, five other cars that you're keeping track of in an intersection that you want to solve over, let's say, 100 time steps. Like that's no problem. I mean, unless you have a really, really weird geometry to the cost function or constraints and you're solving, like you have a terrible warm start. Like I mean, you can make it slow, but
sure.
like the other thing I'd say here is you can really optimize the hell out of this. So like I have a colleague, a co-author, who he built a version of this to run inside of a particle filter. So every single particle update was running this same solver. He wrote it in Julia. He made sure everything was statically allocated, precompiled everything, and he got his solve times down into the microseconds. So like, I mean, it's just one anecdote, obviously, but I'm not concerned about it.
Sure, we're going to move on to the other question that I see from Dave Loper. Programmatically, can we configure game theory models to map to complex deontological and consequential ethical behaviors in AI? For example, I'm aware of existing elements such as forgiveness, niceness, retaliation, clarity. Would you talk about encoding that, or maybe talk about the politeness in your?
Yeah. I think maybe this question is getting a little bit more philosophical than I'm comfortable answering, but I guess I would say let me take the like here's the level at which I'm comfortable answering this question, which would just be that everything I've presented was strictly about the Nash concept, with the exception of that last slide. As long as we're talking about the Nash concept, we are strictly talking about games in which every player has some objective, and given other players' actions or strategies, the other player, I am unilaterally happy with my decision. Now, what my objective is another question. Could be anything you like. So I showed an example where it's, I was trying to construct an objective that encoded, that biased me towards being polite to somebody else. That was just some cooked up example I came up with in 5 minutes. So it's not a big, I mean, I don't know that says any, I don't want to make a philosophical statement based on, 5 minutes worth of David's thought, but I do think that the flexibility afforded by the solution concept is quite significant. You can choose any objective you like. So.
Good. I think we're running out of time. It's 12:10. Thank you so much for your time. I think folks can email in case for other offline questions that we have more. But thank you, Dr. David, for your time. I think you will receive a nice plaque from UND and
Thank you very much.
A certificate from our dean, and in all the time that you've spent. I think it's interesting. I see a lot of opportunities for us to collaborate on even running on these optimization on the edge devices, doing some kind of decomposition strategies, for multiplayer, looking at so we can continue our dialogue offline later. Thank you so much.
Certainly. Thanks so much for having me, and I look forward to continued discussions.
Take care.
Thanks so much. Bye-bye.